Tonight, we're going to explore something that will completely shatter how you understand reality. The speed of light, 300,000 kilometers per second, 186,000 miles per second. But here's what almost nobody truly grasps. Light speed isn't just really fast. It's a cosmic speed limit woven into the fabric of reality itself. It determines how time flows, how space curves, how cause and effect work. And the truly mind-bending part, you cannot go faster. Not with better technology, not with unlimited energy. Not ever. This isn't a challenge waiting to be overcome. It's a fundamental law that shapes everything in our universe, from the largest galaxies to the smallest particles. By the end of tonight, you're going to understand why light speed isn't just a barrier. It's the barrier that defines what's possible and what will forever remain impossible. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Light is everywhere. Right now, photons are bouncing off everything around you, entering your eyes, allowing you to see the world. Light from the sun traveled 93 million miles to reach Earth this morning. Light from your phone screen is hitting your retinas, carrying information. We live in a universe filled with light, bathed in it constantly. And yet, for most of human history, we had absolutely no idea how fast light actually travels. The ancient Greeks debated whether light traveled instantaneously or had a speed. Most believed it was instantaneous. After all, when you open your eyes, you see things immediately, right? There's no delay, no waiting period. You flip a light switch and the room illuminates instantly, so it seemed obvious that light must travel infinitely fast, arriving at your eyes the moment it's emitted. Some thinkers disagreed. Empedocles, a Greek philosopher who lived around 450 BC, suggested that light must take time to travel, even if that time is imperceptibly short. But he had no way to prove it. Aristotle, whose opinions dominated Western thought for nearly 2,000 years, believed light was instantaneous. He argued that light wasn't even a thing that moves. It was simply the presence of a transparent medium. When you introduced a light source, the entire medium became illuminated all at once. This view persisted for centuries. Through the Middle Ages, through the Renaissance, most scholars accepted that light traveled instantaneously. There was no reason to think otherwise based on everyday experience. The world seemed to support this idea at every turn. Lightning and thunder arrive separately, but light from a candle appears the instant you light it. The sun rises and illuminates the landscape without any perceptible delay. Stars twinkle in the night sky, their light seemingly arriving the moment they shine. But in the 1500s and 1600s, as the scientific revolution began, some thinkers started questioning this assumption. The very nature of scientific inquiry was changing. No longer were scholars content to accept ancient wisdom without testing it. They wanted measurements, experiments, evidence. Galileo Galilei, the Italian astronomer who revolutionized our understanding of the cosmos, attempted to measure the speed of light around 1638. His method was simple, even elegant. He and an assistant stood on hilltops several miles apart, each holding a covered lantern. Galileo would uncover his lantern, and the moment his assistant saw the light, the assistant would uncover his own lantern. Galileo would measure how long it took for him to see his assistant's light after uncovering his own lantern. The experiment failed. Galileo detected no measurable delay. He concluded that either light travels instantaneously or it travels so fast that the delay was too small to measure with his equipment. He was right on the second point. The delay over a few miles is only a few millionths of a second, far too brief for human reaction times to detect. Even if Galileo and his assistant had perfect reflexes, even if they could react in zero time, the delay would still be invisible to them. But Galileo's attempt was important. It showed that the question could be asked experimentally. Science wasn't just about philosophical debate anymore. It was about measurement, about testing ideas against reality. Galileo had established a principle. If light has a speed, we should be able to measure it. The fact that he failed didn't mean light was instantaneous. It just meant he needed longer distances or better equipment. The breakthrough came from an unexpected source. In 1676, a Danish astronomer named Ole Rømer was studying Jupiter's moons. Specifically, he was observing Io, the innermost of the 4 large Galilean moons that Galileo had discovered. Io orbits Jupiter every 1.77 days, and as it does, it passes behind Jupiter, disappearing from view. These eclipses happen like clockwork, predictable and regular. Rømer was making detailed observations of these eclipses, recording exactly when they occurred. He was trying to create accurate tables that could be used for navigation, but he noticed something strange. The eclipses didn't happen exactly when predicted. When Earth was closer to Jupiter in its orbit, the eclipses happened slightly earlier than expected. When Earth was farther from Jupiter, they happened later. The discrepancy was only about 22 minutes over the course of Earth's year, but it was consistent and measurable. At first, this might have seemed like an error in the observations or the predictions, but Rømer noticed a pattern. The delays correlated perfectly with Earth's position in its orbit. When Earth was moving toward Jupiter, the eclipses came early. When Earth was moving away, they came late. This wasn't random error. This was systematic. Rømer realized what was happening. Light took time to travel from Jupiter to Earth. When Earth was closer to Jupiter, the light had less distance to travel, so we saw events sooner. When Earth was farther away, the light took longer to reach us, so we saw events later. The eclipses themselves were happening on schedule. It was the light carrying information about those eclipses that was delayed. This was revolutionary. Rømer had proven that light has a finite speed. Using the diameter of Earth's orbit and the timing discrepancy, he calculated that light takes about 22 minutes to cross a distance equal to the diameter of Earth's orbit around the Sun. His calculation wasn't quite accurate because he didn't know the exact size of Earth's orbit, but he was in the right ballpark. He had demonstrated, for the first time in human history, that light doesn't travel instantaneously. The scientific community was divided. Some accepted Rømer's findings immediately. Others remained skeptical, arguing that the delays might be caused by something else. Maybe Jupiter's moons didn't orbit with perfect regularity. Maybe there were unknown gravitational influences affecting their orbits. The debate continued for decades. Over the next 2 centuries, scientists refined measurements of light speed. In 1849, French physicist Hippolyte Fizeau conducted an ingenious experiment using a rapidly rotating toothed wheel. Light would pass through a gap between teeth, travel several kilometers to a mirror, bounce back, and return through the wheel. By adjusting the wheel's rotation speed until the returning light was blocked by the next tooth, Fizeau could calculate light's speed. He got remarkably close to the true value, measuring it at about 313,000 kilometers per second. A few years later, Léon Foucault improved on this with a rotating mirror method. By 1862, he had measured light speed to within 1% of the modern value. His measurement was about 298,000 kilometers per second. The methods were getting more sophisticated, the measurements more precise. By the late 1800s, American physicist Albert Michelson had pushed precision even further. Using an 8-sided rotating mirror and carefully measured distances, he determined light speed to be about 299,790 kilometers per second. His measurements were so precise that they remained the standard for decades. Today, we know the speed of light with extraordinary precision. In a vacuum, light travels at exactly 299,792,400 458 meters per second. That's about 186,282 miles per second. For simplicity, scientists often round this to 300,000 kilometers per second, or 186,000 miles per second. This number isn't an approximation anymore. It's defined. In 1983, scientists decided to define the meter based on the speed of light rather than the other way around. 1 meter is now defined as the distance light travels in 1,299,792,458th of a second. The speed of light is now a fixed constant by definition, and we measure distances based on it. This might seem like a strange choice, but it makes sense. The speed of light is more fundamental than any human-defined unit of length. It's a property of the universe itself. By defining the meter in terms of light speed, we're anchoring our measurements to something constant and universal, rather than something arbitrary like the length of a metal bar in Paris. But what does this speed actually mean? How fast is 186,000 miles per second? Let's start with comparisons to things we understand. A commercial jet flies at about 550 miles per hour. That's fast enough to get you from New York to Los Angeles in about 5 hours. At this speed, you're covering distance quickly by human standards. You can see the landscape below changing, clouds passing by, the curvature of Earth becoming visible if you look carefully. Light travels about 338,000 times faster than a jet airplane. In the time it takes you to snap your fingers, roughly 1/4 of a second, light can travel 75,000 kilometers. That's nearly twice around Earth's equator. In 1 second, light travels 300,000 kilometers, enough to circle Earth's equator about 7.5 times. Let me put this another way. If you could somehow travel at the speed of light, you could go from New York to Los Angeles in about 16 milliseconds. That's 16 thousandths of a second. You could circle Earth at the equator in 134 milliseconds, less time than it takes to blink. You could travel from Earth to the moon in about 1.3 seconds. The fastest car ever built, the Thrust SSC, reached a top speed of about 1,228 kilometers per hour. That's about 763 miles per hour, faster than the speed of sound. At this speed, you could drive across the United States in about 3.5 hours. It's incredibly fast by human standards. Light travels about 870,000 times faster than this. The Thrust SSC, breaking the sound barrier, generating shockwaves, pushing the limits of what wheels and engines can do, is crawling compared to light. The fastest human-made object ever created is the Parker Solar Probe, launched in 2018 to study the sun. At its maximum speed, when it's close to the sun and using the sun's gravity to accelerate, it reaches about 192 kilometers per second. That's about 430,000 miles per hour, about 630 times faster than the Thrust SSC. It's incredibly fast. Fast enough to travel from Earth to the moon in about 33 minutes. Fast enough to cross the United States in about 20 seconds. And yet, even at this record-breaking speed, the Parker Solar Probe is only traveling at about 0.064% of the speed of light. Light is still more than 1,500 times faster. The probe is crawling by comparison. If the Parker Solar Probe were a person walking, light would be a jet fighter screaming past at supersonic speed. When you turn on a flashlight, photons stream out of the bulb at light speed. They cross the room in a few billionths of a second, so fast that there's no perceptible delay. As far as your brain is concerned, the light appears instantly. The room goes from dark to illuminated in what seems like 0 time. But light doesn't actually travel instantly. It takes time, and over cosmic distances, that time adds up. The moon is about 384,000 kilometers from Earth. Light from the moon takes about 1.3 seconds to reach us. This means when you look at the moon, You're seeing it as it was 1.3 seconds ago. Not a huge delay, but a delay nonetheless. The moon you're looking at is the moon from slightly in the past. When astronauts walked on the moon during the Apollo missions, their radio communications had to cross this distance. Radio waves are electromagnetic radiation, just like visible light, and they travel at the same speed. Every time an astronaut spoke, their words took 1.3 seconds to reach Mission Control in Houston. Mission Control's reply took another 1.3 seconds to return to the moon. This created a nearly 3-second delay in every exchange. You can hear it in the recordings. The astronaut says something. There's a pause. Mission Control responds. There's another pause. Then the astronaut hears the response and replies. The conversation has this strange rhythm to it, this lag that reminds you that they're not in the same room. They're not even on the same world. They're separated by 250,000 miles of empty space, and even radio waves traveling at the fastest possible speed need time to bridge that gap. The sun is about 150 million kilometers from Earth. Light from the sun takes about 8 minutes and 20 seconds to reach us. Think about that. When you look at the sun during the day, when you feel its warmth on your skin, you're not experiencing the sun as it is right now. You're experiencing the sun as it was more than 8 minutes ago. If something dramatic happened on the sun right now, if it suddenly changed color or dimmed or even exploded, we wouldn't know for 8 minutes and 20 seconds. The event would occur, but the light carrying information about that event would still be traveling through space toward Earth. We'd keep seeing the sun as it was, not as it is, for over 8 minutes. Then suddenly, we'd see the change. This is a profound realization. It means the universe we observe is not the universe as it exists right now. It's a historical record. Every photon that enters your eye is a messenger from the past, carrying information about how things were, not how things are. This gets more dramatic as we look at more distant objects in our solar system. Mars, depending on where it is in its orbit, is between 55 million and 400 million kilometers from Earth. At its closest, light from Mars takes about 3 minutes to reach us. At its farthest, it takes about 22 minutes. This creates real problems for space exploration. When NASA operates rovers on Mars, there's always a significant communication delay. Commands sent from Earth take 3 to 22 minutes to reach the rover, depending on Mars's position. Data from the rover takes the same amount of time to come back. You can't drive a Mars rover in real time the way you'd drive a remote-controlled car on Earth. The delay is too long. Instead, engineers have to plan the rover's activities carefully, send a sequence of commands, and then wait to see what happens. If the rover encounters a problem, if it gets stuck on a rock, or its wheel gets caught, the problem might exist for 20 minutes or more before anyone on Earth even knows about it. Then engineers have to analyze the situation, figure out a solution, write new commands, send them to Mars, and wait again. A problem that might take 30 seconds to solve with a remote-controlled car on Earth could take an hour or more to solve on Mars. This is why Mars rovers need to be semi-autonomous. They need onboard computers that can recognize obstacles, avoid hazards, and make basic decisions without waiting for instructions from Earth. The Perseverance rover, which landed on Mars in 2021, has sophisticated autonomous navigation. It can analyze the terrain ahead, plot a safe path, and drive for significant distances without human intervention. This autonomy is necessary because the light speed delay makes real-time control impossible. Saturn, the beautiful ringed gas giant, is about 1.4 billion kilometers from Earth at its closest. Light from Saturn takes about 80 minutes to reach us. When the Cassini spacecraft was orbiting Saturn from 2004 to 2017, every image it took, every measurement it made, took 80 minutes to travel back to Earth. Scientists couldn't control Cassini in real time. They had to program entire sequences of commands, days or weeks in advance, and trust that the spacecraft would execute them correctly. When Cassini made its final plunge into Saturn's atmosphere on September 15th, 2017, the spacecraft had already been destroyed for 80 minutes before scientists on Earth received the final signal. They watched the data stream in, knowing they were witnessing the death of the spacecraft, as it had happened more than an hour ago. There was something poignant about this delay, this reminder that even our fastest communication is limited by light speed. Neptune, the farthest planet from the Sun, is about 4.5 billion kilometers away. Light from Neptune takes about 4 hours to reach Earth. If you could somehow stand on Neptune and look back at Earth with a powerful telescope, you'd be seeing Earth as it was 4 hours ago. And if you tried to have a conversation with someone on Earth, each exchange would take 8 hours. You'd say something, wait 4 hours for your words to reach Earth, and then wait another 4 hours for the reply to come back. These delays are frustrating, but they're also profound. They remind us that space is vast, and information can only travel so fast. Light speed is the fastest possible speed in the universe. Nothing can go faster. And even at this maximum speed, crossing the solar system takes hours. Crossing interstellar space takes years. The nearest star to our Sun is Proxima Centauri, about 4.24 light years away. A light year is the distance light travels in 1 year, which is about 9.46 trillion kilometers. So, Proxima Centauri is about 40 trillion kilometers from Earth. Light from Proxima Centauri takes 4.24 years to reach us. When you look at Proxima Centauri through a telescope, you're seeing it as it was over 4 years ago. If Proxima Centauri exploded today, we wouldn't see the explosion until 4 years from now. The star could already be gone, and we'd have no way of knowing. We'd keep seeing it shining peacefully in the sky, completely unaware that it no longer exists. For 4 years, we'd be observing a ghost, a star that died but whose light is still in transit. Sirius, the brightest star in the night sky, is about 8.6 light years away. The light you see from Sirius tonight left that star in the year 2016. Betelgeuse, the red supergiant in Orion, is about 700 light years away. The light you see from Betelgeuse tonight left that star in the year 1325, during the Middle Ages on Earth, long before the Renaissance, before the printing press, before the discovery of the Americas. When that light began its journey, the Aztec Empire was just forming in Mexico, and the Black Death hadn't yet arrived in Europe. This is one of the most profound implications of light speed. It connects distance and time in a fundamental way. When you look out into space, you're looking back in time. The farther away something is, the older the light you're seeing. The night sky isn't just a map of space. It's a timeline, a history book showing you the universe at different ages. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.5 million light years away. The light you see from Andromeda tonight left that galaxy 2.5 million years ago, when early humans were just beginning to use stone tools on Earth. Australopithecus was walking upright in Africa. Our ancestors were learning to make basic tools, to use fire, to communicate in primitive ways, and light was already traveling from Andromeda toward Earth, carrying information about that distant galaxy across the void. The most distant galaxies we've observed are more than 13 billion light years away. The light from these galaxies has been traveling through space for most of the age of the universe. We're seeing these galaxies as they were when the universe was young, less than 1 billion years after the Big Bang. These galaxies formed from the first generations of stars, containing only hydrogen and helium with trace amounts of heavier elements. They're nothing like the mature galaxies we see nearby today. Light speed determines what we can see and when we can see it. It creates a cosmic horizon beyond which we cannot look, not because our telescopes aren't powerful enough, but because light from beyond that horizon hasn't had time to reach us yet. Every observation we make is an observation of the past. Astronomy is history. We can never see the present state of distant objects. We can only see how they were. And this is just the beginning. Light speed isn't just about how fast light travels. It's about how the universe works at the most fundamental level. It's about the relationship between space and time, between cause and effect, between what's possible and what isn't. Because here's the truly mind-bending part. Nothing can travel faster than light. Not spaceships, not particles, not information. Light speed is the universe's ultimate speed limit. And this speed limit isn't a technological problem waiting to be solved. It's built into the very structure of reality itself. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would revolutionize physics. His name was Albert Einstein, and the paper was titled On the Electrodynamics of Moving Bodies. Today, we know it as the theory of special relativity. This wasn't just another scientific paper. It was a complete reimagining of space, time, and motion. Einstein's theory answered a question that had been troubling physicists for years. The question was this: why does light always travel at the same speed, regardless of how fast you're moving? This seems strange at first. In everyday life, speeds add together in predictable ways. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, someone standing on the ground sees the ball moving at 70 kilometers per hour. The speeds add. This is so obvious, so intuitive, that we never question it. It's been tested countless times in everyday experience. It's how velocity addition works in the world we know. But light doesn't work this way, and this fact had been puzzling scientists for decades. If you're on a spacecraft moving at half the speed of light and you shine a flashlight forward, the light doesn't travel at 1.5 times the speed of light. It travels at exactly the speed of light, both from your perspective on the spacecraft and from the perspective of someone watching you from Earth. The same exact speed, 300,000 kilometers per second, measured by both observers. This seems impossible. How can the light be moving at the same speed for both observers when one observer is already moving at half the speed of light? The math doesn't work, unless you change what you mean by speed. Speed is distance divided by time. If you want light to travel at the same speed for different observers, you have to accept that distance and time are not absolute. They can't be the same for everyone. They have to adjust, to bend, to change, depending on your motion. This was Einstein's breakthrough. He showed that space and time are not separate, independent things. They're unified into a single, four-dimensional structure called space-time. And how you experience space and time depends on how you're moving through space-time. The faster you move through space, the slower you move through time relative to someone who's stationary. This isn't an illusion or a measurement error. Time literally passes more slowly for you. Clocks run slower. Biological processes slow down. Aging slows down. From your perspective, time feels normal. A second still feels like a second. But from the perspective of someone watching you, your time has slowed down. Your clock is ticking more slowly than theirs. This effect is called time dilation, and it's one of the most thoroughly tested predictions in all of physics. It's been confirmed by countless experiments over the past century. It's not speculation. It's not theory in the sense of being unproven. It's observed fact, as well established as gravity or electromagnetism. Here's a simple thought experiment to understand time dilation. Imagine you're on a spacecraft with a special clock. This clock consists of two mirrors facing each other with a beam of light bouncing between them. Each time the light completes one round trip, that's one tick of the clock. This is called a light clock, and it's a useful way to visualize how time works. From your perspective on the spacecraft, the light travels straight up and down between the mirrors. If the mirrors are 1 meter apart, and light travels at 300,000 kilometers per second, each tick takes a very small fraction of a second. Everything seems normal to you. The clock ticks at a regular rate. Now, imagine someone on Earth watches your spacecraft zoom past at, say, 90% the speed of light. From their perspective, the light in your clock isn't traveling straight up and down. Because the spacecraft is moving, the light traces out a diagonal path. It has to travel both up and sideways to keep up with the moving mirrors. The diagonal path is longer than the straight up and down path. You can prove this with basic geometry. If the spacecraft moves sideways while the light travels up, the light has to cover both the vertical distance and match the horizontal motion. The total path length is greater, but light still travels at the same speed for both observers. That's the fundamental rule. Light always travels at 300,000 kilometers per second, no matter who measures it or how they're moving. So if the light has to travel a longer path but can't go faster, it must take more time to complete each round trip. From Earth's perspective, your clock is ticking more slowly than an identical clock on Earth. Time itself is passing more slowly for you. This isn't just a property of light clocks. All clocks slow down the same amount. Mechanical clocks, atomic clocks, biological clocks. Your heartbeat slows down. Your thoughts slow down. Your aging slows down. Time itself is dilated. If you're moving at 90% light speed relative to Earth, every process in your body, every chemical reaction, every vibration of every atom, all of it happens more slowly from Earth's perspective. At 90% the speed of light, time dilation becomes significant. For every year that passes on your spacecraft, about 2.3 years pass on Earth. If you traveled at this speed for what feels like 10 years to you, you'd return to Earth to find that 23 years had passed. Your friends and family would be much older. Children you left behind would be adults. You'd have traveled into their future. The effect gets more extreme as you approach light speed. At 99% the speed of light, time passes about 7 times slower for you. 1 year for you equals 7 years on Earth. At 99.9%, it's about 22 times slower. At 99.99%, it's about 71 times slower. If you could somehow travel at 99.9999999% the speed of light, you could travel to a star 100 light years away. From Earth's perspective, the journey would take 100 years, but from your perspective, due to extreme time dilation, the journey might take only a few months. You'd experience a few months aboard the spacecraft, but when you arrived, 100 years would have passed in the rest of the universe. Everyone you knew would be dead. Civilizations would have risen and fallen. The world would have moved on without you. This has been tested experimentally many times. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners. The clocks that flew east, moving faster relative to Earth's surface, showed less elapsed time than clocks that stayed on the ground. The clocks that flew west, moving slower relative to Earth's rotation, showed more elapsed time. The differences were tiny, measured in nanoseconds, but they matched Einstein's predictions exactly. Time dilation at everyday speeds is incredibly small, but it's real and measurable with precise instruments. GPS satellites provide an even better demonstration. These satellites orbit Earth at about 14,000 kilometers per hour, high above the atmosphere. At this speed, time dilation causes their onboard clocks to run about 7 microseconds slower per day than clocks on Earth. 7 microseconds doesn't sound like much, but GPS requires extraordinary precision. Light travels about 300 meters in 1 microsecond. If GPS didn't account for time dilation, your GPS navigation would accumulate errors of several meters per day, and within a few hours, your location would be off by several kilometers. The fact that GPS works, that it can pinpoint your location to within a few meters, is proof that time dilation is real and must be corrected for. But time dilation isn't the only strange effect. There's also length contraction. Objects moving at high speeds actually become shorter in the direction of motion as measured by a stationary observer. Imagine a spaceship that's 100 meters long when it's parked. If it accelerates to 90% the speed of light, someone on Earth measuring it would find that it's only about 44 meters long. The spaceship has contracted. It's been squeezed in the direction of motion. From the perspective of people on the spaceship, everything feels normal. The ship still feels 100 meters long to them. They can walk from front to back and measure 100 meters. But Earth observers would measure it as being shorter. At 99.999% the speed of light, the contraction is extreme. A 100-meter spaceship would appear to be less than 1 meter long to Earth observers. It would be flattened almost into a pancake, compressed in its direction of motion to a tiny fraction of its rest length. This contraction is real. It's not an optical illusion. It's not that the spaceship looks shorter because of how light reaches your eyes. It actually is shorter, as measured by rulers and instruments. The space inside the spacecraft has contracted. Particles in particle accelerators really do contract as they approach light speed, and this contraction affects how they interact with matter and with detectors. There's also a third effect: relativistic mass increase. Well, that's not quite the right way to phrase it, and modern physicists avoid this terminology. What actually happens is that as an object approaches light speed, its inertia increases. It becomes harder and harder to accelerate it further. The amount of force required to produce a given acceleration increases without limit. In practical terms, this means that as you approach light speed, it takes more and more energy to go even a tiny bit faster. To actually reach light speed would require infinite energy, which is impossible. The universe doesn't contain infinite energy. Therefore, nothing with mass can ever reach the speed of light. Light itself can only reach light speed because photons have no rest mass. They're fundamentally different from particles like electrons or protons. This has been demonstrated in particle accelerators countless times. Scientists can accelerate particles like protons or electrons to speeds incredibly close to light speed. The Large Hadron Collider, the world's most powerful particle accelerator, accelerates protons to 99.999999% the speed of light. That's 6 nines after the decimal point. But notice all those nines. Despite using enormous amounts of energy, despite magnets so powerful they could lift an aircraft carrier, despite a ring 27 kilometers around containing thousands of superconducting magnets cooled to near absolute zero, the particles never quite reach light speed. They get closer and closer, but there are always more nines to add. You can approach light speed asymptotically, getting closer and closer but never actually reaching it. And the energy required grows exponentially. To accelerate a proton from 99% light speed to 99.9% requires far more energy than accelerating it from 0 to 99%. All that energy just to add one more 9. To go from 99.9% to 99.99% requires even more. Each additional 9 costs more than all the previous 9s combined. For a macroscopic object, something with real mass like a spaceship or even a grain of sand, the energy requirements become absurd. To accelerate 1 kilogram of matter to 99.999%, the speed of light would require more energy than the entire annual energy consumption of human civilization. That's 1 kilogram, about the mass of a textbook. To accelerate a spacecraft with crew, supplies, and equipment, you'd need millions or billions of times more energy. And you'd still be traveling slower than light. To reach actual light speed would require infinite energy. It's not just impractical, it's impossible. The laws of physics don't allow it. You'd need more energy than exists in the entire universe. This is why light speed is called the universal speed limit. It's not that we haven't figured out how to go faster yet. It's not that we need better rockets or more advanced technology. It's that faster is fundamentally impossible for anything with mass. The universe has a maximum speed, and that speed is light speed. Photons, particles of light, can travel at light speed because they have zero rest mass. From the moment they're created to the moment they're absorbed, they travel at exactly light speed. They can't speed up or slow down in a vacuum. It's simply what photons do. It's their nature. They have no choice. But anything with mass, no matter how small, can never reach light speed. Not with current technology, not with future technology, not ever. The energy required becomes infinite as you approach the limit. There's no way around this. It's not an engineering problem. It's a fundamental feature of how the universe works. Einstein's equations show why this happens. The relationship between energy, momentum, and mass is given by E squared equals P squared C squared plus M squared C to the fourth, where E is energy, P is momentum, M is mass, and C is the speed of light. As velocity approaches light speed, momentum approaches infinity for any object with mass. To have infinite momentum requires infinite energy. The universe doesn't contain infinite energy, therefore, nothing with mass can reach light speed. As your speed increases relative to a stationary observer, three things occur simultaneously. Time slows down for you, lengths contract in your direction of motion, and your inertia increases. All three effects grow without limit as you approach light speed, and all three effects conspire to prevent you from ever reaching it. They're not separate phenomena. They're different aspects of the same underlying reality, the structure of space-time itself. The universe has a maximum speed, and that speed is light speed, 300,000 kilometers per second, 186,000 miles per second. That's it. That's the fastest anything can ever go through space. Nothing can exceed it. Nothing can even reach it unless it has zero mass. This speed limit has profound consequences. It means that interstellar travel, the kind of space exploration we see in science fiction, is incredibly difficult. The distances between stars are measured in light years. Even traveling at a significant fraction of light speed, which is already beyond our current technology by orders of magnitude, journeys to other stars would take years or decades. And that's for the nearest stars. Most stars are much farther away. The Milky Way galaxy is 100,000 light years across. Even traveling at light speed, which is impossible for anything with mass, it would take 100,000 years to cross our galaxy. You'd need to travel for longer than all of recorded human history just to get from one side to the other. Andromeda, the nearest large galaxy, is 2.5 million light years away. Even at light speed, the journey would take 2.5 million years, and you can't go faster than light speed, ever. No matter what technology you develop, no matter what discoveries you make, the light speed limit is absolute. This creates a fundamental barrier to exploring the universe. The cosmos is vast, and information can only travel at light speed. No matter how advanced our technology becomes, we're limited by this cosmic speed limit. We can't go around it. We can't exceed it. We can only work within it. Some people hope that future technology might find a way around this. Maybe we'll discover warp drives or wormholes, or some other exotic phenomenon that allows faster than light travel. We'll explore these possibilities later. But for now, understand this. According to everything we know about physics, according to a century of experiments and observations, according to our most fundamental theories of how reality works, light speed is the limit. It's not a challenge to overcome. It's a fundamental feature of how the universe works. The speed of light determines the structure of space-time itself. It determines how cause and effect work. It determines what you can know and when you can know it. It determines how time flows and how space is measured. It determines the maximum rate at which information can propagate through the universe. Light speed isn't just the speed at which light travels. It's the speed at which all massless particles travel. It's the speed at which gravity propagates. If the sun suddenly disappeared, we wouldn't feel the change in gravity for 8 minutes and 20 seconds, the same time it takes light from the sun to reach us. Gravity travels at light speed. It's not instantaneous. It propagates as ripples in space-time, moving outward at exactly the speed of light. It's also the speed at which information can travel. Any cause and effect relationship is limited by light speed. You cannot affect something instantaneously if it's far away. The effect propagates outward at light speed, and not faster. This is crucial for maintaining causality, the principle that causes precede effects. This creates what physicists call the light cone. Every event in space-time has a past light cone, containing all the events that could have caused it, and a future light cone, containing all the events it could potentially affect. These cones expand at light speed. Events outside your light cone are causally disconnected from you. They cannot affect you, and you cannot affect them. They might as well not exist from your causal perspective. This is profoundly important. It means the universe has structure. Events are not all causally connected. There are regions of space that are fundamentally unreachable, not just practically but in principle. Information from those regions can never reach you because it would have to travel faster than light, which is impossible. The observable universe, the portion of the universe we can see, is defined by light speed and the age of the universe. Light from anything farther than a certain distance hasn't had time to reach us yet. The edge of the observable universe is a light speed horizon. Beyond that horizon, there might be more universe, perhaps infinitely more, but we can never see it, never interact with it, never know anything about it, because the light hasn't reached us yet and never will, given how fast space is expanding. Light speed isn't just a speed. It's the fundamental limit that structures reality itself. It determines what's possible and what isn't. It creates boundaries that can never be crossed. It isolates regions of the universe from each other in ways that no technology can overcome. Cosmic rays provide another beautiful demonstration of time dilation. These are high-energy particles, mostly protons, that bombard Earth's atmosphere from space. When they hit molecules in the upper atmosphere, they create showers of secondary particles, including particles called muons. Muons are interesting because they're unstable. They decay very quickly. The average muon lives for about 2.2 microseconds before decaying into other particles. 2.2 microseconds is incredibly brief. Even traveling at close to the speed of light, a muon should only be able to travel about 660 meters before decaying. The problem is that muons are created about 15 kilometers up in the atmosphere. They should decay long before reaching the ground. And yet, we detect muons at ground level all the time. Detectors in labs, in classrooms, anywhere on Earth's surface register muons constantly. How is this possible? The answer is time dilation. From our perspective on Earth, the muons are traveling at about 99.5% the speed of light. At this speed, time passes about 10 times more slowly for the muons. What's 2.2 microseconds from the muon's perspective becomes about 22 microseconds from our perspective. This extra time is enough for the muons to reach the ground before decaying. From the muon's perspective, something different is happening. The muon experiences its normal 2.2 microsecond lifetime, but from its perspective, Earth is rushing toward it at 99.5% light speed. And due to length contraction, the 15-kilometer distance has contracted to about 1.5 kilometers. The muon only needs to travel 1.5 kilometers in its reference frame, which it can do in 2.2 microseconds at near light speed. Both perspectives give the same result. Muons reach the ground, but one invokes time dilation and the other invokes length contraction. They're two ways of looking at the same phenomenon. This is the beauty of relativity. Different observers see different things, but everyone agrees on what actually happens. And this brings us to perhaps the most troubling implication of light speed: cosmic loneliness. Even if the universe is filled with intelligent civilizations, the vast distances and the light speed limit might mean that we can never meaningfully interact with them. We're isolated by the very structure of space-time itself. But that's a topic for the next section. Let's talk about what light speed means for our relationship with the cosmos. Because once you truly understand that nothing can travel faster than light, once you accept that this isn't a temporary limitation, but a permanent feature of reality, the implications are staggering. They affect everything from how we explore space, to whether we'll ever meet alien civilizations, to the very nature of the universe we can observe. First, let's consider what light speed means for looking at the universe. When you look at anything, you're seeing it as it was in the past, not as it is now. The light had to travel from the object to your eyes, and that journey takes time. For nearby objects, this delay is negligible. The delay between your friend standing 3 meters away and the light from them reaching your eyes is about 10 nanoseconds, 10 billionths of a second. Your brain can't detect this delay. It's effectively instantaneous from your perspective. Your entire everyday experience suggests that sight is instantaneous. But as distances grow, so does the delay. And at cosmic distances, the delays become enormous. When you look at the Andromeda galaxy through a telescope, you're seeing photons that left that galaxy 2.5 million years ago. You're literally looking back in time. Andromeda, as you see it tonight, is Andromeda from the distant past, from an era when early humans were just beginning to use stone tools on Earth. If something dramatic happened in Andromeda today, if a star exploded, if an entire star cluster suddenly changed, if a supermassive black hole flared to life, we wouldn't see it for 2.5 million years. The event would occur, the light would begin its journey across space, traveling at the maximum possible speed, and it would still take millions of years to reach us. By the time we saw it, human civilization might have risen, flourished, and vanished. Entire species might have evolved and gone extinct on Earth. The world would have transformed completely, and only then would we see what happened in Andromeda today. Now scale this up. The most distant galaxies we've observed are more than 13 billion light years away. The light we see from them today left those galaxies when the universe was less than 1 billion years old. We're seeing these galaxies as they were in their infancy. They might look completely different now. They might have merged with other galaxies, formed trillions of new stars, developed complex structures, or they might have been torn apart by collisions, their stars scattered, their gas consumed. We have no way of knowing. The information about their current state is still traveling toward us through space, and it won't arrive for billions of years. Actually, we'll never see the current state of those distant galaxies, because the universe is expanding, and that expansion is accelerating. By the time light from those galaxies' current state reaches Earth, those galaxies will have changed again. We'll always be looking at the past, never the present. We're forever chasing information that's always ahead of us, always out of reach. This creates a profound limitation on our knowledge. We can only see the past. We can never see the present state of distant objects. The farther away something is, the older our view of it. The universe we observe is not the universe as it exists right now. It's a historical record, a museum of cosmic history, with the most distant objects being the oldest exhibits. There's an edge to what we can see, a cosmic horizon called the edge of the observable universe. This edge is about 46.5 billion light years away in all directions. Why 46.5 billion and not 13.8 billion, the age of the universe? Because space itself has been expanding. Galaxies that emitted light 13.8 billion years ago have moved much farther away during the time their light was traveling toward us. When light left those distant galaxies 13.8 billion years ago, they were much closer to us than 46.5 billion light years. But as the light traveled through space, space itself was stretching, carrying those galaxies farther away. By the time the light reaches us, the galaxies that emitted it are now 46.5 billion light years away, and they're receding from us faster than the speed of light. Not because they're moving through space faster than light, but because the space between us and them is expanding faster than light can cross it. But here's what's crucial. This edge is not the edge of the universe. It's just the edge of what we can see. The actual universe is almost certainly much larger, possibly infinite. But we can never see beyond this horizon because light from beyond it hasn't had time to reach us yet. And it gets worse. The universe's expansion is accelerating, driven by something we call dark energy. This mysterious force, which makes up about 68% of the universe's total energy content, is pushing space apart faster and faster. Distant galaxies are moving away from us at ever-increasing speeds. There are galaxies right now whose light will never reach us. Ever. They're receding faster than their light can close the gap. Space between us and them is expanding faster than light can travel through it. These galaxies are beyond what's called the cosmic event horizon. We will never see them, never know they exist, never be able to interact with them in any way. They're causally disconnected from us forever. And as the universe continues to expand, as dark energy continues to accelerate that expansion, more and more galaxies will slip beyond this horizon, disappearing from our view permanently. Galaxies we can see today will fade away, their light redshifted to longer and longer wavelengths until they simply vanish from our telescopes. Billions of years in the future, perhaps 100 billion years from now, if any observers exist then, they'll look out at a much emptier universe. Most galaxies will have been carried beyond the horizon by the expansion of space. Future astronomers might see only their own galaxy, and perhaps a few nearby companions that have merged with it, with nothing else visible in any direction. The sky will be dark except for the stars of their own galaxy. They'll live in what appears to be a lonely, empty universe, unaware of the trillions of galaxies that existed but are now forever beyond their view. These future astronomers might not even be able to discover the Big Bang. The cosmic microwave background radiation, the afterglow of the Big Bang that we can still detect today, will have redshifted to such long wavelengths that it will be undetectable. The evidence for the universe's origin will have literally moved beyond reach. Future scientists might believe the universe is static and eternal, unaware of its explosive beginning, because the evidence will have disappeared beyond the horizon. But let's bring this back to something more immediate: space exploration and the search for life. Light speed creates massive challenges for both. Consider a mission to Mars. Mars is, on average, about 225 million kilometers from Earth. Light takes about 12.5 minutes to travel this distance. When Mission Control on Earth sends a command to a Mars rover, that command takes 12.5 minutes to arrive. The rover executes the command, and any response takes another 12.5 minutes to return to Earth. That's a 25-minute round-trip time for communication. This makes real-time control impossible. You can't steer the rover remotely the way you'd steer a drone on Earth. The delay is too long. By the time you see an obstacle on your screen and react, the rover has already hit it. Instead, rovers on Mars have to be semi-autonomous. Engineers program sequences of actions, upload them, and trust the rover to execute them. If something goes wrong, the rover has to recognize the problem and either fix it or stop and wait for new instructions from Earth. This is why Mars rovers move so slowly. The Perseverance rover, one of the most advanced rovers ever built, typically travels at about 150 meters per hour when driving autonomously. That's about the speed of a very slow walk. It could physically move much faster, but it needs time to analyze the terrain, identify hazards, and plot a safe path. Because if it makes a mistake, 25 minutes will pass before anyone on Earth knows about it, and another 25 minutes before corrective commands arrive. Now, consider a mission to the outer solar system. When New Horizons flew past Pluto in July 2015, Pluto was about 4.8 billion kilometers from Earth. Light took about 4.5 hours to travel this distance. New Horizons had to execute its entire Pluto flyby sequence autonomously. Mission controllers uploaded the commands days in advance, and then waited. During the critical flyby, they couldn't do anything. They couldn't adjust the spacecraft's trajectory, couldn't change which instruments were operating, couldn't respond to any problems. They just had to wait for the data to start arriving, 4.5 hours after the actual flyby occurred. The spacecraft had to be smart enough to handle everything on its own, and it was. The flyby was a spectacular success, returning stunning images of Pluto's surface, its atmosphere, its moons, but it illustrates the challenge. The farther you go, the longer the communication delay, and the more autonomous your spacecraft must be. Now let's think about interstellar missions. The nearest star, Proxima Centauri, is 4.24 light-years away. A radio signal to a spacecraft orbiting a planet there would take 4.24 years to arrive. A response would take another 4.24 years. That's an 8.5-year round trip for a single exchange of information. Imagine trying to operate a rover on a planet orbiting Proxima Centauri. You see something interesting and send a command to investigate. 4 years later, the rover receives your command and investigates. 4 years after that, you receive the data. The investigation you requested happened 4 years ago, and you're only learning about it now. If something went wrong, if the rover encountered a problem, if it broke down or got stuck, 8 years would pass before you even knew about it and could attempt a solution. By that time, the situation would have changed completely. Batteries would be dead, systems would have failed, the mission would likely be over. Any interstellar mission would have to be almost completely autonomous. It would have to make decisions on its own, respond to situations as they arise, complete its mission without real-time guidance from Earth. The communication delay is simply too long for anything else. The spacecraft would need artificial intelligence far more sophisticated than anything we have today. It would need to be able to analyze situations, make decisions, troubleshoot problems, adapt to unexpected circumstances, all on its own, light years from home. But at least information can travel at light speed. Physical travel is much worse. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object. It's been traveling for nearly 50 years at about 17 kilometers per second, fast enough to cross the United States in about 4 minutes. And in all that time, traveling continuously through the vacuum of space with nothing to slow it down, it's traveled about 24 billion kilometers. That sounds like a lot. 24 billion kilometers. But it's only about 0.27% of a light year. After nearly 50 years of travel, Voyager 1 hasn't even covered 0.3% of the distance to the nearest star. At its current speed, Voyager 1 would need about 73,000 years to reach Proxima Centauri, and it's not even aimed in that direction. If Voyager 1 were heading straight for Proxima Centauri instead of out into interstellar space in a different direction, and if it maintained its current speed for the entire journey, it would arrive around the year 75,000. To put that in perspective, 73,000 years ago, modern humans were living in small tribal groups during the Ice Age. We were hunter-gatherers using stone tools. We hadn't invented agriculture, writing, cities, nations, or any of the structures we think of as civilization. All of human history, everything from the first farms to the present day, has happened in less time than it would take Voyager 1 to reach the nearest star. The fastest spacecraft we've built, the Parker Solar Probe, reaches speeds up to 192 kilometers per second when it's closest to the Sun. At this speed, it would still take about 6,800 years to reach Proxima Centauri. That's longer than all of recorded human history. Writing was invented about 5,000 years ago. You could have launched a Parker Solar Probe speed mission when humans first learned to write, and it still wouldn't have arrived yet. The ancient Sumerians could have sent a probe to Proxima Centauri, and we'd still be waiting for it to arrive. And this is just to reach the nearest star. Most stars are much farther away. The Milky Way galaxy is 100,000 light years across. Even traveling at light speed, which is impossible for anything with mass, crossing our galaxy would take 100,000 years. At the speed of our fastest current spacecraft, it would take over 300 million years. That's longer than the dinosaurs existed on Earth. There have been proposals for faster interstellar spacecraft. The Breakthrough Starshot Initiative, announced in 2016 by physicist Stephen Hawking and investor Yuri Milner, proposes using powerful ground-based lasers to accelerate tiny spacecraft to about 20% of light speed. The concept is elegant. You build a spacecraft that's essentially a computer chip with a camera, weighing maybe a gram, attached to an ultra-thin light sail made of reflective material, perhaps only a few atoms thick. Then you point massive arrays of lasers at it from Earth. The laser light pushes on the sail, and because the spacecraft is so incredibly light, it can be accelerated to tremendous speeds. At 20% light speed, which is about 60,000 kilometers per second, a probe could reach Proxima Centauri in about 20 years. Add another 4 years for the signal to return to Earth, and you could potentially get data from Proxima Centauri within 24 years of launch. That's within a human lifetime. You could be involved in launching the mission and still be alive when the data returns. That's exciting, but the engineering challenges are enormous, perhaps insurmountable with current or near-future technology. First, you need incredibly powerful lasers. The proposal calls for a laser array with a total power of about 100 gigawatts. That's roughly the output of 100 nuclear power plants, all focused into a laser beam a few kilometers wide. This beam would need to track the tiny spacecraft as it accelerates, keeping the light precisely focused on the sail. Any deviation and the sail would drift out of the beam and the acceleration would stop, leaving the spacecraft coasting at whatever speed it had reached. The laser would need to operate for only a few minutes to accelerate the spacecraft to 20% light speed. But during those minutes, it would need to deliver an enormous amount of energy with pinpoint precision to a target that's moving faster and faster, eventually receding at tens of thousands of kilometers per second. The targeting and tracking systems would need to be extraordinarily sophisticated. Second, the spacecraft needs to survive the journey. At 20% light speed, you're moving at 60,000 kilometers per second. At this speed, collisions with even tiny particles become catastrophic. A speck of dust, something smaller than a grain of sand, hitting the spacecraft at this speed would release energy equivalent to a large bomb. The kinetic energy is proportional to velocity squared, so high speeds make even tiny impacts devastating. The spacecraft would need shielding to protect it, but any shielding adds weight, and weight is the enemy when you're trying to accelerate something with light pressure. The more the spacecraft weighs, the more power you need to accelerate it, and the equation gets worse and worse as you add weight. It's a vicious circle. You need shielding to survive, but shielding makes you heavier, which makes you harder to accelerate, which means you need more laser power, which makes the whole system more expensive and difficult. Third, you need to be able to communicate with the spacecraft over 4 light years of distance. The tiny probe would need a laser or radio transmitter powerful enough to send a detectable signal across that distance. At 4 light years, any signal spreads out enormously. The inverse square law means that signal strength decreases with the square of the distance. A signal that's strong at 1 light year is 16 times weaker at 4 light years, not 4 times weaker. To send data back to Earth from Proxima Centauri, the spacecraft needs a transmitter that can generate a signal strong enough to be detected across this distance. And you have to fit this capability into a spacecraft the size of a computer chip. It's like trying to shout across an ocean and be heard clearly on the other side, except the ocean is 4 light years wide. Fourth, you need to actually hit Proxima Centauri's star system and fly past it at the right distance and angle to get useful data. At 20% light speed, the spacecraft is traveling so fast that it crosses the orbit of Mars in about 40 minutes. The entire width of our solar system from the Sun to Neptune is crossed in about 6 hours. You get one shot. There's no slowing down, no course corrections once you're up to speed, because slowing down would require just as much energy as speeding up, and you don't have that energy available in a spacecraft weighing a gram. The spacecraft flies past Proxima Centauri at 60,000 kilometers per second, has maybe a few hours, or at most a few days when it's close enough to take useful pictures and measurements, and then continues on into the void, never to be seen again, drifting through interstellar space forever. A human artifact traveling between the stars for eternity. So while breakthrough starshot is an interesting concept, and it's based on real physics rather than science fiction, it remains highly theoretical. The technology doesn't exist yet, and there are formidable challenges that might be impossible to overcome. Even if we somehow built such a craft and successfully sent it tomorrow, it would be at least 20 years before it reached Proxima Centauri, and another 4 years before we got any data back. That's a 24-year round trip for information, assuming everything works perfectly, which in the history of space exploration has never been a safe assumption. And this is just to reach the nearest star. With technology we can actually build today, the kind of spacecraft we know how to engineer and launch with current rockets and current materials and current computer systems, getting to Proxima Centauri would take not decades, but millennia. We'd need to build multi-generational spacecraft, massive vessels that could support human crews for thousands of years. These generation ships would be cities in space. They'd need to grow food, recycle water and air, maintain complex systems, support a population large enough to avoid genetic problems from inbreeding, and keep that population motivated to continue a journey that would span dozens or hundreds of generations. The people who arrived at Proxima Centauri would be the distant descendants of those who launched, perhaps hundreds of generations removed, living in a world they'd never left, traveling to a destination they'd only heard about in stories passed down through the centuries. The challenges of building such a ship are immense. You need a closed ecosystem that can support human life indefinitely. Nothing can be wasted. Water must be recycled perfectly. Air must be regenerated. Food must be grown continuously. Any failure in these systems means death for everyone aboard. And these systems must work not for years or decades, but for millennia. You need to prevent genetic problems from inbreeding in a small population. A generation ship might carry a few thousand people at most. Over hundreds of generations, genetic diversity would decline unless carefully managed. You'd need genetic engineering, careful breeding programs, or perhaps frozen genetic material to maintain diversity. You need to maintain social stability over multiple generations. How do you prevent rebellion, revolution, religious conflicts, wars? The inhabitants of a generation ship can't leave. They're trapped together for their entire lives. Conflicts that on Earth might be resolved by people moving away can't be resolved that way on a generation ship. You're stuck with everyone forever. You need to ensure that descendants still want to complete the mission their ancestors started. What if, 50 generations in, the inhabitants decide they don't want to go to Proxima Centauri anymore? What if they want to turn around and go home, or settle on some asteroid along the way, or just drift through space indefinitely? The original mission objectives might seem irrelevant to people who were born in space, have never seen Earth, and have no personal connection to the reasons the mission was launched. Some have proposed suspended animation, or cryogenic freezing. Put the crew to sleep for the journey and wake them at the destination. This would solve many problems. No need for decades of life support. No psychological issues from long confinement. No generational drift in mission objectives. You go to sleep on Earth, wake up at Proxima Centauri. But we don't know if this is possible. Can human bodies survive being frozen for decades or centuries? What about cellular damage from ice crystal formation? When water freezes, it expands, and ice crystals can rupture cell membranes. Various organisms on Earth can survive freezing by producing antifreeze compounds, but humans don't have this capability naturally. What about the effects on the brain? Consciousness, memory, personality, all of these arise from the precise connections between billions of neurons. If those connections are damaged by freezing, would you wake up as the same person? Would you wake up at all? Would you retain your memories, your personality, or would you wake up as someone fundamentally different if you woke up at all? These are unsolved problems that might not have solutions. We've frozen and revived small organisms, even some organs for transplant. But freezing and reviving an entire human, especially for years or centuries, is far beyond our current capabilities. It might be impossible. The reality is that interstellar travel with humans aboard might simply be impractical, given the constraints imposed by light speed. We might be confined to our own solar system for the foreseeable future, perhaps permanently. Our solar system is our cosmic island, and the distances to other islands are simply too vast to cross with any foreseeable technology. That doesn't mean we can't explore other star systems with robotic probes. Machines don't need life support, don't suffer psychological problems from isolation, don't care if the journey takes centuries. But human exploration of other stars, the kind of exploration where people travel there and see alien worlds with their own eyes, might remain forever in the realm of science fiction. And this brings us to one of the most profound questions in science. Where is everybody? If the universe contains billions of galaxies, each with billions of stars, and if planets are common around those stars, and if life arises wherever conditions are right, then there should be countless intelligent civilizations out there. Some should be millions or billions of years older than us. They should be visible. We should see signs of them. Radio signals, laser pulses, massive engineering projects, Dyson spheres harvesting the energy of entire stars, something. But we don't. The universe appears to be silent. We've been listening with radio telescopes for decades. We've scanned millions of stars. We've looked for technosignatures, signs of advanced technology, and we've found nothing. No signals, no structures, no evidence of anyone else. The cosmos is quiet. This is the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" during a lunch conversation in 1950. There are many proposed solutions to this paradox. Maybe intelligent life is incredibly rare. Maybe the jump from simple life to complex life is extraordinarily difficult. Maybe intelligence rarely develops even when complex life exists. Maybe technological civilizations destroy themselves shortly after developing technology, wiped out by nuclear war or environmental collapse or artificial intelligence or something else we haven't thought of yet. Maybe they're out there but staying quiet. Maybe they've learned that broadcasting your presence is dangerous. Maybe there are predator civilizations that hunt for signals from younger civilizations. Maybe advanced species stay silent to avoid detection. Maybe they communicate in ways we can't detect. We've been listening for radio signals because that's what we use. But maybe advanced civilizations use something else. Quantum communication, neutrino beams, gravitational waves, technologies we haven't imagined yet. Maybe we're like someone trying to find modern civilization by looking for smoke signals. We're looking, but we're looking for the wrong thing. Or maybe the answer is simpler and more sobering. Space is too big, and light speed is too slow. Even if civilizations are common, The distances between stars might be so vast that contact is effectively impossible. A radio signal traveling at light speed would take years, decades, centuries, or millennia to reach even nearby stars. A reply would take just as long. Meaningful communication becomes impossible over these timescales. Think about trying to have a conversation with a civilization 10 light years away. You send a message, "Hello, we are humans from Earth. We'd like to exchange information." 20 years later, you might receive a reply, "Greetings, we are pleased to make contact." You respond with questions about their science, their culture, their history. Another 20 years pass before you receive answers. Each exchange takes 40 years. You could ask a question as a young researcher and receive the answer when you're about to retire. You could spend your entire career on a single conversation, exchanging perhaps 10 or 20 messages total. Any kind of real-time dialogue is impossible. Any kind of collaboration on time-sensitive issues is impossible. And if you wanted to physically travel to that civilization, even traveling at a significant fraction of light speed, the journey would take decades. By the time you arrived, generations would have passed on both worlds. The civilization you set out to visit might have changed dramatically. The reasons for the visit might no longer be relevant. For more distant civilizations, separated by hundreds or thousands of light years, the situation is even worse. A signal sent to a civilization 1,000 light years away wouldn't receive a response for 2,000 years. You could send a message and neither you, nor your children, nor your grandchildren, nor dozens of generations of your descendants would live to see the reply. Only your distant ancestors, living in a world you could barely imagine, might hear back from the distant civilization. If you sent a message today to a civilization 1,000 light years away, your message would arrive around the year 3025. If they responded immediately, the reply would arrive around the year 5025. Human civilization as we know it might not even exist by then. We might have transformed into something unrecognizable, or destroyed ourselves, or evolved into a completely different form. The answer would arrive to a world that had forgotten the question. The universe might be filled with civilizations that are forever isolated from each other by the tyranny of distance and the light speed limit. Each civilization develops alone, asks its questions alone, makes its discoveries alone, and eventually dies alone, never knowing that others existed nearby in cosmic terms, but impossibly far away in practical terms. The cosmic web of galaxies, superclusters, and filaments might also be a web of isolation, where intelligent species are trapped in their own regions of space, unable to reach out, unable to make contact, separated by distances that even light takes millennia to cross. This is the cosmic loneliness imposed by light speed. Even if we're not alone in the universe, we might be effectively alone because the barriers to communication and travel are simply too great to overcome. The light speed limit doesn't just constrain how fast we can go, it constrains what we can know, who we can meet, and how connected we can be to the broader universe. We've established that nothing can travel faster than light. The laws of physics, specifically Einstein's special and general relativity, forbid it. As you approach light speed, time slows down, length contracts, and your inertia increases without limit. Reaching light speed would require infinite energy. It's impossible, but humans are creative. We don't like being told something is impossible. Throughout history, we've overcome barriers that seemed insurmountable. We've learned to fly, to split the atom, to land on the moon, to peer into the quantum realm. So maybe, just maybe, there's a way around the light speed limit. Maybe there's a loophole we haven't discovered yet. Physicists and science fiction writers alike have proposed various ways to circumvent the light speed limit. Let's examine these proposals carefully and see if any of them actually work. Let's separate science from fiction, possibility from fantasy. The most famous proposal is the warp drive, popularized by Star Trek. The idea is elegant. Instead of moving through space at faster than light speeds, you warp space itself. You contract space in front of your ship and expand space behind it. The ship remains stationary relative to the space immediately around it, but the bubble of space containing the ship moves through the larger universe faster than light. This sounds like cheating, but it's actually consistent with general relativity, at least mathematically. General relativity, Einstein's theory of gravity, says nothing can move through space faster than light, but it doesn't prohibit space itself from expanding or contracting at any speed. In fact, during cosmic inflation, a fraction of a second after the Big Bang, space expanded much faster than light, not because anything was moving through space faster than light, but because space itself was expanding at an extraordinary rate. So, could we create a warp drive? In 1994, Mexican physicist Miguel Alcubierre published a paper showing that, mathematically, a warp drive is possible within the framework of general relativity. The Alcubierre drive, as it's now called, would contract space in front of a spacecraft and expand it behind, creating a wave of space-time that carries the ship along. From the perspective of someone on the ship, they're not moving. Space is moving around them. Sounds great, right? We found a loophole in the laws of physics. We can travel faster than light without violating relativity. Not so fast. The Alcubierre drive has several massive, probably insurmountable problems. First, it requires exotic matter with negative energy density. To create the space-time distortion needed for a warp drive, you need matter that has negative mass energy. As far as we know, such matter doesn't exist. Some quantum effects produce tiny amounts of negative energy in very specific circumstances, like the Casimir effect, where two metal plates placed very close together in a vacuum show a slight attractive force. But this produces incredibly tiny amounts of negative energy, nowhere near what the Alcubierre drive would need. Second, even if exotic matter exists, you'd need an enormous amount of it. Early calculations by Alcubierre suggested you'd need more mass energy than exists in the entire observable universe to power a warp drive capable of carrying a spacecraft across interstellar distances. More mass energy than in all the galaxies, all the stars, all the planets, all the gas and dust combined. Obviously impossible. Later refinements by physicist Chris van den Broek and others reduced this to only the mass energy of Jupiter. Still impossible with any conceivable technology, but at least not more than the universe impossible. Jupiter has a mass of about 2 times 10 to the 27th kilograms. Converting that entirely to energy would require first assembling Jupiter's entire mass in one place, then somehow converting it all to negative energy, then using it to power a warp drive. We can't do any of these things. Third, there are causality problems. If you can travel faster than light, even through a warp drive loophole, you can potentially send information backward in time. Here's how this works. Imagine you send a message faster than light from Earth to a distant star, then someone on that star, which is moving relative to Earth due to the rotation of the galaxy and other motions, sends a reply back faster than light. Because of how relativity works, because different observers in different reference frames disagree about what events are simultaneous, it's possible for the reply to arrive back at Earth before the original message was sent. You'd have backward-in-time communication, which violates causality. You could receive an answer before asking the question. You could know the outcome of an event before it happens. This creates paradoxes. Some physicists argue that the laws of physics must prohibit any form of faster-than-light travel for this reason. If you could send information faster than light, you could create causality violations, which would make the universe inconsistent and paradoxical. The universe seems to protect causality by making faster-than-light travel impossible through any means. Fourth, and perhaps most fundamentally, Creating an Alcubierre drive would require you to manipulate space-time itself on enormous scales. You'd need to generate a gravitational field strong enough to distort space by significant amounts over distances of many meters or kilometers. This requires either enormous masses comparable to planets or stars, or technologies that can harness exotic physics we don't understand. Even if we solved all these problems, even if exotic matter exists and we figured out how to create and control it, even if we prevented causality violations somehow, there's still a practical issue. How do you create the warp bubble in the first place? Once you're inside a warp bubble, traveling faster than light, you're causally disconnected from the space outside. You can't send signals out to control the bubble. You can't adjust your trajectory. You can't stop. The bubble would need to be controlled from outside, but if you're moving faster than light, no signal from outside can catch up to you to provide control. Some calculations suggest you'd need to set up the destination before you left. You'd need to pre-position exotic matter at your target location to create the warp field there. But if you need to visit your destination before you can warp there, what's the point? You'd need slower than light travel to set up the warp infrastructure, which defeats the purpose. The Alcubierre drive is mathematically possible within general relativity, appearing as a valid solution to Einstein's field equations. But physically, it faces obstacles that are probably insurmountable. Most physicists consider it a curiosity, an interesting mathematical solution that doesn't correspond to anything achievable in reality. It's a bit like discovering that the laws of physics allow a perpetual motion machine mathematically, but only if you have access to impossible materials and infinite energy. What about wormholes? These are shortcuts through space-time, tunnels connecting two distant locations. Fall into one end, emerge instantly from the other end, even if the two ends are light years apart in normal space, like a cosmic subway system that bypasses all the space in between. Wormholes also appear in the equations of general relativity. They're mathematically possible as solutions to Einstein's field equations. A wormhole is essentially a tunnel through higher dimensional space connecting 2 points in our three-dimensional space. You could travel from one point to another by going through the wormhole rather than across normal space. But just like warp drives, wormholes require exotic matter to remain stable. A naturally occurring wormhole, if one existed, would collapse immediately, crushing anything trying to pass through it. The throat of the wormhole, the narrow section connecting the two ends, would pinch off faster than light could cross it. To keep a wormhole open, you'd need matter with negative energy density, propping it open, preventing it from collapsing. And even if you could create and stabilize a wormhole, there are causality problems similar to those with warp drives. If you have a wormhole connecting 2 points in space, and one end is moving relative to the other, or if the two ends experience different gravitational time dilation, you can create a situation where entering one end sends you back in time. Here's how it works. Imagine you create a wormhole connecting Earth and a distant star. Then you take one end of the wormhole and accelerate it to near light speed, then bring it back to Earth. Due to time dilation, less time passes for the moving end than for the stationary end. Now you have two ends of the wormhole sitting near each other on Earth, but they're at different times. Enter one end, and you exit the other end at an earlier time. You've created a time machine. Again, this violates causality and creates paradoxes. You could go back in time and prevent yourself from entering the wormhole in the first place. The famous grandfather paradox. You could go back and kill your own grandfather before your father was born, preventing your own existence, which means you couldn't have gone back to kill him, which means you do exist, which means you could go back to kill him, and so on in an infinite loop of contradiction. Some physicists propose a chronology protection conjecture. The laws of physics must prevent time travel to protect causality. Therefore, the laws must prevent wormholes from being used as time machines. How would this work? Perhaps quantum effects would destabilize any wormhole that could be used for time travel. Perhaps the energy fluctuations from virtual particles would grow uncontrollably in a time machine configuration, destroying the wormhole. Perhaps negative energy cannot exist in sufficient quantities to stabilize both a wormhole and a time machine. Perhaps something we don't understand yet makes wormholes impossible or prevents them from being used for faster-than-light travel. The bottom line is that wormholes, while allowed by the mathematics of general relativity, probably don't exist in reality. Or if they do exist naturally on quantum scales, they're far too small to be useful for macroscopic travel. The Planck length, about 10 to the minus 35 meters, might contain tiny quantum wormholes that form and collapse constantly due to quantum fluctuations, but these would be impossibly small, far smaller than atoms, far smaller than anything we could ever use for travel. Using a wormhole for travel would require creating an artificial wormhole, stabilizing it with exotic matter, and keeping it open long enough to pass through. All of these steps face enormous obstacles. Most physicists consider wormhole travel to be even less plausible than warp drives. Science fiction often invokes hyperspace, an alternate dimension where the laws of physics are different and faster than light travel is possible. You enter hyperspace, travel quickly to your destination through this alternate realm, and exit back into normal space far from where you started. It's a convenient plot device that allows characters to zip around the galaxy without worrying about light speed limitations. But is it real? There's no evidence whatsoever that hyperspace exists. The concept doesn't arise from any physical theory. It's pure speculation, created by science fiction authors to explain faster-than-light travel without worrying about the details of how it actually works. Some theories in physics do propose extra dimensions beyond the 3 spatial dimensions we experience. String theory, for instance, requires 9 or 10 spatial dimensions, with 6 or 7 of them compactified to tiny sizes we can't perceive. These extra dimensions might exist at every point in space, curled up so small that even electrons can barely move through them. But these extra dimensions don't work like hyperspace in science fiction. They're not alternate realms you can enter and exit at will. They're additional directions in space, perpendicular to the 3 dimensions we know, but curled up so tightly that traveling through them is impossible for anything larger than fundamental particles. It's like trying to walk down a hallway that's only 1 nanometer wide. You physically can't fit. There's no evidence for these extra dimensions, and even if they exist, they don't provide a way to circumvent the light speed limit. They're part of the same space-time structure, governed by the same laws of physics, including the prohibition on faster-than-light travel. Hyperspace, as depicted in science fiction, a parallel dimension you can jump into and travel through faster than light, has no basis in real physics. It's a storytelling device, not a scientific possibility. What about quantum entanglement? This is a real phenomenon where 2 particles can be connected in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and worried it might violate the light speed limit. If measuring a particle here instantly affects a particle on the other side of the galaxy, isn't information traveling faster than light? No. Quantum entanglement cannot be used to send information faster than light. Here's why. When you measure an entangled particle, you get a random result. If you measure the spin of an electron, you might get spin up or spin down with equal probability. You can't control which result you get. It's fundamentally random. The other entangled particle, when measured, will give a correlated result. If your particle is spin up, the other will be spin down, or vice versa depending on how they were entangled. But the person measuring the other particle also sees a random result. They can't tell that their result is correlated with yours until you communicate through normal, slower than light means and compare results. To send information, you need to be able to choose what signal to send. I'll send a 1 by doing this, and a 0 by doing that. But with quantum entanglement, you can't choose. The measurements are random, You can only observe. You can't encode a message in random data. Quantum entanglement is weird and counterintuitive, showing that quantum mechanics allows correlations that seem impossible from a classical perspective. But it doesn't violate causality or allow faster-than-light communication. It's consistent with special relativity. The correlation between entangled particles isn't transmitted from one to the other. The correlation exists from the moment the particles become entangled, and measurements simply reveal it. No information travels between the particles when they're measured. There's also no evidence that consciousness or thought can travel faster than light. Some people suggest that since we don't fully understand consciousness, maybe it operates outside the laws of physics. Maybe thoughts can travel instantly across space. Maybe telepathy is real and works through some unknown mechanism. But there's no reason to think this. Consciousness arises from brain activity, which involves neurons firing, chemicals diffusing, electrical signals propagating. All of these processes are subject to the laws of physics, including the light speed limit. Brain activity can be measured with EEG, fMRI, and other tools. It's physical. It obeys physical laws. Thoughts propagate through your brain at speeds much slower than light. Neurons can fire at most about 1,000 times per second. Signals in your nervous system travel at speeds ranging from less than 1 meter per second for unmyelinated neurons to about 120 meters per second for fast myelinated neurons. That's incredibly slow compared to light speed, which is 300 million meters per second. If thoughts could travel faster than light, your brain wouldn't need neurons. Information could jump instantly from one part of your brain to another, but it doesn't. Your brain is limited by the same physical laws as everything else. What about tachyons? These are hypothetical particles that always travel faster than light. If such particles existed, according to special relativity, they would have imaginary mass. Not negative mass, but imaginary mass, as in the square root of -1. Their energy-momentum relationship would be different from normal particles. More importantly, there's no evidence that tachyons exist. Despite decades of searching, no one has ever detected a tachyon or any phenomenon that would require tachyons to explain. And if they did exist, it's not clear how you could use them for faster-than-light travel or communication. You can't slow a tachyon down to below light speed any more than you can accelerate a normal particle to above light speed. The light speed barrier works both ways. It separates slower than light particles from faster than light particles, and neither type can cross it. Some people point to cosmic inflation, the rapid expansion of space in the first fraction of a second after the Big Bang, as proof that faster than light travel is possible. During inflation, space expanded faster than light. Doesn't this show that the light speed limit can be violated? No. During inflation, space itself expanded. Nothing moved through space faster than light. This is a crucial distinction. The light speed limit applies to motion through space, not to the expansion of space itself. Space can expand at any rate. During inflation, it expanded exponentially, doubling in size every tiny fraction of a second. But objects within that space were not moving through space faster than light. From the perspective of any object, nearby objects were receding slowly. It's only when you looked at very distant objects that the accumulated expansion made them appear to recede faster than light, and this is still allowed by relativity. We can't harness cosmic inflation for travel. Inflation happened once, in the very early universe, and it stopped. We don't know what caused it to start, we don't know why it stopped, and we certainly don't know how to restart it locally to propel a spacecraft. Even if we did, it wouldn't help us travel anywhere. It would just make space bigger, expanding everything, including the distance to our destination. After examining all these proposals, the conclusion is clear. Every proposed method of faster-than-light travel either requires exotic matter that probably doesn't exist, violates causality in ways that should be impossible, relies on phenomena we have no evidence for, or is pure speculation with no connection to real physics. After a century of testing special and general relativity in countless experiments, after confirming time dilation in particle accelerators and GPS satellites, after verifying length contraction in cosmic ray observations, after checking every prediction and finding them all correct, the conclusion is inescapable. The light speed limit is real, it's fundamental, and there's no way around it. This might seem depressing. We're stuck with a cosmic speed limit that makes interstellar travel incredibly difficult and intergalactic travel essentially impossible. We can never explore more than a tiny fraction of the universe. We're isolated by the vast distances and the light speed barrier. But maybe this limitation is actually important. Maybe it's what makes the universe stable and comprehensible. Without the light speed limit, causality breaks down. Cause and effect lose meaning. You could affect events before they happened. You could create paradoxes where effects precede causes, where you prevent your own existence, where the timeline becomes tangled and contradictory. The universe would descend into chaos. The light speed limit protects causality. It ensures that causes precede effects. It creates structure in space-time, dividing events into past, present, and future. It gives time a direction, an arrow that points from past to future. Without it, the universe might be incomprehensible, unstable, perhaps even impossible. The light speed limit also creates locality. Events at one location can only affect nearby events immediately. Distant effects take time to propagate, spreading outward at light speed. This locality is fundamental to how the laws of physics work. It's why we can do experiments in a lab without worrying about influences from distant galaxies. It's why cause and effect have clear, traceable relationships that we can study and understand. If information could travel faster than light, locality would break down. Distant events could instantaneously affect nearby events. The clean separation between here and there, between now and then, would disappear. Physics would become impossibly complicated, perhaps impossible to understand at all. Every event would be potentially influenced by every other event in the universe simultaneously. There would be no isolation, no independence, no way to study one thing without considering everything. So maybe the light speed limit isn't a flaw in the universe's design. Maybe it's a feature. Maybe it's necessary for a universe that's stable, comprehensible, and capable of supporting complexity in life. Maybe the universe needs this limit to function properly. And there's something humbling about the light speed limit. It reminds us that we're not in control of the universe. We don't get to decide how fast information travels or how space-time works. We're subject to laws larger than ourselves. Laws that existed long before we did and will continue long after we're gone. For billions of years, light has been traveling through space at exactly the same speed, unaffected by what it passes through, uninfluenced by the stars and galaxies around it. This constancy is part of what makes the universe work. If light speed changed, if it varied from place to place or time to time, if it depended on the motion of the source or the observer in ways beyond what relativity predicts, the universe would be chaotic and unpredictable. The light speed limit also gives us perspective on our place in the cosmos. We're confined to a tiny corner of a vast universe. We can see billions of galaxies, but we can never visit most of them. We're like islanders who can see distant lands across an ocean but can never sail to them because the ocean is too wide and the journey too long. This isolation forces us to make choices. If we can only explore a tiny fraction of the universe, which part do we explore? If we can only send messages that take years or centuries to arrive, what do we say? If our reach is limited, what do we do with the reach we have? Perhaps the light speed limit teaches us to value what's nearby. Our solar system, while vast by human standards, is a tiny neighborhood in cosmic terms. It's the region we can actually explore with reasonable effort. Mars is only minutes away by light-speed communication. The outer planets are only hours away. The Kuiper Belt, while distant, is still reachable within a human lifetime. Within our solar system, we're not limited by light speed in any practical sense. We're limited by rocket technology, by life support, by radiation shielding, by the challenges of living in space, but not by information delay. We can communicate with spacecraft throughout the solar system with delays measured in minutes or hours, not years. So maybe we focus here first. Maybe we learn to thrive in our solar system before worrying about the stars. Maybe we build habitats on the moon, Mars, the moons of Jupiter and Saturn. Maybe we mine asteroids for resources, build space stations, establish colonies throughout our cosmic neighborhood. Maybe we learn to live off-world, to make space our home, not just a place we visit briefly. The light speed limit doesn't prevent any of this. It only prevents us from easily reaching other stars. And maybe that's okay. Maybe our future, at least for the next few centuries or millennia, lies in our solar system. Maybe we need to master local space before we worry about interstellar space. And who knows? Maybe someday, thousands or millions of years from now, we'll find something we don't expect. Maybe there's some aspect of physics we don't understand yet, some loophole we haven't discovered. Maybe future civilizations will look back at our certainty that faster than light travel is impossible and smile at our limited understanding, the way we smile at ancient people who thought Earth was the center of the universe. But based on everything we know now, based on a century of experiments and observations, based on our best theories of how the universe works, theories that have been tested more thoroughly than almost any others in science, the light speed limit is real and fundamental. It's not a challenge to overcome. It's a law of nature we must accept and work within. 300,000 kilometers per second, 186,000 miles per second. That's the speed of light. That's the maximum speed for anything in the universe. That's the barrier that structures space-time, protects causality, maintains locality, and isolates distant regions of the cosmos from each other. It's the limit that breaks our brains because it's so counterintuitive, so different from our everyday experience where we can always go faster if we try. But it's also the limit that makes the universe comprehensible, stable, and beautiful. We cannot go faster. We cannot circumvent it. We cannot cheat. We're bound by this limit as surely as we're bound by gravity, by entropy, by the arrow of time. And in accepting this limit, in understanding it deeply, in working within its constraints, we gain a deeper appreciation for the universe we inhabit and our place within it. The speed of light isn't just a speed. It's the fundamental constant that determines what's possible and what isn't. It's the boundary between the accessible and the forever unreachable. It's the limit that defines reality itself. And now you understand it. Not just as a number, not just as a trivia fact, but as a profound feature of the cosmos. You understand why nothing can go faster, what this limit means for exploring space, for searching for life, for understanding the universe. You understand why it's not a temporary obstacle but a permanent feature of reality. The universe operates at light speed. Information propagates at light speed. Causality respects light speed. Time dilation, length contraction, mass energy equivalence, all of these arise from light speed. And we, living in this universe, must accept this fundamental limit. The speed of light is the limit that breaks our brains because it violates every intuition we have about speed and motion. But it's also the limit that makes everything possible. The limit that allows the universe to exist in a stable, comprehensible form. Thank you for joining me on this journey through the nature of light speed and the structure of space-time. If you found this exploration valuable, please like this video and subscribe to the channel. It helps me create more content like this. And the next time you flip a light switch or see the sun rise or look up at the stars, remember what you've learned tonight. Those photons traveled at the maximum possible speed to reach you. They're messengers from across space and time, carrying information at the universe's ultimate speed limit. Light speed isn't just fast. It's the speed at which reality itself operates. It's the cosmic constant that binds space and time together, that maintains causality, that structures the universe from the smallest quantum scale to the largest cosmic structures. And now you know why nothing, absolutely nothing, can ever go faster. Good night, and may you never look at light the same way again.